There is a rule in chemistry. One of those rules so fundamental, so deeply woven into our understanding of how the universe works, that scientists stopped questioning it a long time ago. When you find nickel in space, you find iron, always. This is not a guideline. It is not a suggestion. It is a law written in the nuclear furnaces of dying stars, etched into every meteorite that has ever fallen to Earth, confirmed in every comet we have ever studied. Iron and nickel are cosmic siblings, forged together in the violent deaths of massive suns, scattered across the galaxy in supernova explosions that predate our solar system by billions of years. In the Sun, iron outnumbers nickel by roughly 18 to 1. In asteroids, in the dusty hearts of comets, in the ancient meteorites that crash through our atmosphere, this ratio holds. It has held for as long as we have been measuring it, until now. On the 1st of July, 2025, a telescope in the Chilean desert detected a faint smudge of light moving against the stars. The telescope, part of NASA's Asteroid Terrestrial Impact Last Alert System, was designed to scan the sky for dangerous objects headed toward Earth. What it found instead was something from outside our solar system entirely, something that had been traveling through the void between stars for billions of years, something that, when scientists finally got a good look at it, did not play by the rules. They named it 3I/Atlas, the third interstellar object ever confirmed, and it was glowing with nickel, but not iron. The scientists who first noticed this did not immediately raise alarms. Spectroscopic anomalies happen. Instruments malfunction. Data gets corrupted. The natural response was to assume error and wait for confirmation. The confirmation came. And then came more observations from different telescopes using different instruments, operated by different teams on different continents. The Keck Observatory in Hawaii, the European Southern Observatory in Chile, the Gemini telescopes on 2 hemispheres. All of them saw the same thing. 22 distinct emission lines from nickel atoms blazing against the darkness of space, and no corresponding signal from iron. This was not noise. This was not an artifact. This was a chemical signature that, according to everything we thought we knew about the universe, should not exist. Before we go further, we need to establish what 3I/Atlas actually is. It is a comet. This much is not in dispute, despite what you may have read on certain corners of the internet. A comet is defined by its activity, by the way it responds to solar heating. When 3I/Atlas drew close enough to the sun for its frozen surface to warm, it began to outgas. Ice transformed directly into vapor, a process called sublimation, and that vapor carried dust particles with it, forming a fuzzy envelope around the solid nucleus. This envelope is called the coma. 3I/Atlas has a coma. It has a tail. It brightens as it approaches the sun and dims as it recedes. Its trajectory shows non-gravitational acceleration, the signature of outgassing, acting like a tiny rocket thruster, pushing the comet in ways that pure gravity cannot explain. By every metric we use to classify celestial objects, 3I/Atlas is a comet. But it is not a comet from our solar system. The distinction matters enormously. Our solar system contains trillions of comets, most of them locked in the distant reaches of the Oort cloud, a spherical shell of icy bodies extending perhaps 2 light years from the sun. These comets share a common origin. They formed from the same primordial disk of gas and dust that gave birth to the sun and planets 4.5 billion years ago. Their chemistry, while varied, reflects that shared heritage. 3. I/Atlas, formed somewhere else entirely, around a different star in a different protoplanetary disk, under conditions we can only infer from the chemical evidence it carries. It is a sample of another world delivered to our doorstep by the patient mechanics of gravity and time. And that sample is telling us something unexpected. To understand why this matters, you need to understand what we thought we knew about comets. A comet, at its most basic, is a frozen relic, a time capsule from the birth of a solar system. When a star forms from a collapsing cloud of gas and dust, the leftover material slowly clumps together. Close to the star, where temperatures are high, only rock and metal can survive. But farther out, in the cold outer reaches, volatile compounds can freeze. Water becomes ice. Carbon dioxide crystallizes into solid form. Carbon monoxide, ammonia, methane, they all lock into a frozen matrix alongside dust and rocky debris. These distant snowballs never get the chance to become planets. They are too small, too far from the gravitational currents that shape larger worlds. So they drift. Some fall inward, heated by a passing star, and their ices begin to sublimate, transforming directly from solid to gas, creating the spectacular tales that ancient humans interpreted as omens. Others are flung outward by gravitational encounters with giant planets ejected into the interstellar void, doomed to wander between the stars for eternity. 3I/Atlas is one of these wanderers. Based on its trajectory and its speed, scientists estimate it was ejected from its home star system somewhere between 3 and 11 billion years ago. To put that in perspective, our own solar system is about 4.6 billion years old. 3. I/Atlas may have been sailing through the galaxy before the Earth even existed, before the sun ignited, before the cloud of gas and dust that would become our cosmic neighborhood had even begun to collapse. It carries within it a chemical record of an alien solar system, a message in a bottle from a star we will never identify, written in the language of frozen molecules and ancient ice. And part of that message, when scientists finally decoded it, made no sense. The discovery itself was almost routine, at least at first. The Atlas survey, operated by the University of Hawaii and funded by NASA, scans the entire night sky every 24 hours using a network of telescopes, 2 in Hawaii, 1 in Chile, 1 in South Africa. Together, they constitute humanity's early warning system for potentially hazardous asteroids, objects that might one day threaten Earth. On July 1st, 2025, the Chilean telescope flagged an anomaly. A point of light was moving against the background stars, shifting position over the course of a few hours. This is how we find moving objects in the solar system. The stars appear fixed because they are so far away. Anything closer, anything orbiting the sun, will drift noticeably from night to night, or even hour to hour. The initial trajectory fit suggested the object might be a near-Earth asteroid, the kind of thing that justifies the survey's existence. Observations were immediately submitted to the Minor Planet Center, the International Clearinghouse for newly discovered solar system objects. But within hours, something strange became apparent. The object was moving too fast. Speed is the key to interstellar objects. Everything in our solar system is gravitationally bound to the sun. tracing elliptical orbits that curve back upon themselves. Even comets on highly elongated orbits eventually return, pulled back by the sun's gravity after centuries or millennia in the outer darkness. An interstellar object is different. It approaches from outside, carrying the velocity it had in interstellar space. As it falls toward the sun, it accelerates, gaining speed from the gravitational potential energy, but it never slows down enough to be captured. It swings around and departs, following a hyperbolic trajectory, a curve that opens outward and never closes. The mathematics are unambiguous. If an object's velocity exceeds a certain threshold at a given distance from the sun, it cannot be on a bound orbit. It must have come from outside and must be headed back out. 3I/Atlas exceeded that threshold by a wide margin. Its hyperbolic excess velocity, the speed it will have once it escapes the sun's gravitational influence entirely, is 58 kilometers per second. For comparison, Oumuamua, the first interstellar object, had a hyperbolic excess velocity of about 26 kilometers per second. This made 3I/Atlas the fastest interstellar visitor ever recorded. And that speed has implications. Velocity in interstellar space is a clock. The faster an object moves, the more time it has spent accumulating kinetic energy from gravitational interactions, being flung from star to star, acquiring speed with each encounter. 3I/Atlas's extreme velocity suggests it has been wandering for a very, very long time. Some estimates put its age at 7 billion years. Others go as high as 11 billion. The uncertainty is large, but even the conservative estimates make 3I/Atlas older than the Sun. This is an object that was born in another era of cosmic history, when the Milky Way was younger, when different stars dominated the galactic neighborhood, when the chemistry of interstellar space might have been subtly different from what it is today. And it was coming directly toward us, not toward Earth specifically. There was never any danger of collision, but toward the inner solar system, where our telescopes could study it, where the warmth of the sun would awaken whatever dormant chemistry it carried, where we could finally get a good look at something from beyond. The timing was fortunate. 3I/Atlas arrived during a golden age of astronomical instrumentation. The James Webb Space Telescope was fully operational, its infrared eyes capable of detecting molecules and temperatures that no ground-based observatory could match. The Vera Rubin Observatory, still commissioning, was already demonstrating its unprecedented survey capabilities. A network of ground-based telescopes, from the giant mirrors of Hawaii and Chile to smaller instruments scattered around the globe, stood ready to track anything that moved across the sky. Had 3I/Atlas arrived 50 years earlier, we would have seen a fuzzy dot, maybe noticed its unusual speed, and watched helplessly as it disappeared back into the darkness. Had it arrived 50 years later, we might have sent a spacecraft to intercept it, but it arrived now, in this narrow window, when we can observe in exquisite detail, but cannot yet reach out and touch. That is the tragedy of 3I/Atlas. Close enough to tantalize, too far to sample. A gift we can admire, but never fully unwrap. Within 48 hours of the initial detection, the astronomical community mobilized. Telescope time is precious. Major observatories are booked months or years in advance, with researchers competing fiercely for limited hours on the world's most powerful instruments. But interstellar objects change everything. They are one-time events. They pass through once and never return. The window to study them is measured in months, not years. When word spread that 3I/Atlas was confirmed as interstellar, directors at observatories around the world began clearing schedules. Directors' discretionary time reserved for exactly these kinds of unexpected discoveries was invoked at facilities from Hawaii to Chile to the Canary Islands. Within a week, data was flowing in from dozens of telescopes. The first paper was published on July 3rd, just 2 days after discovery. 40 co-authors from institutions across 4 continents. They confirmed the interstellar trajectory, reported the first photometric measurements, and noted something intriguing. The object appeared fuzzy, not point-like, suggesting it was surrounded by a coma of gas and dust. 3I/Atlas was an active comet, the second interstellar comet ever observed after 2I/Borisov in 2019. But unlike Borisov, which behaved much like an ordinary solar system comet, 3I/Atlas would prove to be full of surprises. Rohan Rahatgaonkar was a doctoral student at the Pontificia Universidad Católica de Chile. His specialty was comet chemistry, specifically the spectroscopic signatures of gases escaping from cometary nuclei. When the interstellar visitor was confirmed, he was part of the international team that scrambled to train the European Southern Observatory's Very Large Telescope on the object. The Very Large Telescope sits atop Cerro Paranal in the Atacama Desert, 2,600 meters above sea level, in one of the driest places on Earth. The air there is so still and so clear that astronomers can peer into the depths of the cosmos with unprecedented precision. And in late July of 2025, they pointed one of its instruments at 3I/Atlas. What they found was atomic nickel. This, by itself, was surprising, but not unprecedented. In 2021, astronomers had made a startling discovery. Nickel and iron vapor existed in the atmospheres of comets from our own solar system, even when those comets were far from the sun, in regions of space too cold for metals to sublimate directly from solid to gas. This finding challenged existing models of cometary chemistry. Metals should not be floating around as vapor at temperatures of 150 Kelvin, that is negative 123 degrees Celsius, cold enough to freeze carbon dioxide solid. Yet there they were. The proposed explanation involved something called metal carbonyls, compounds where metal atoms bond with carbon monoxide molecules. Nickel tetracarbonyl and iron pentacarbonyl are both highly volatile, meaning they can transition from solid to gas at relatively low temperatures. If these compounds formed inside comets, they could sublimate and then break apart under ultraviolet sunlight, releasing free metal atoms into the surrounding gas cloud. The chemistry was exotic but plausible, and crucially, in every solar system Comet studied, nickel and iron appeared together in roughly equal amounts. But 3I/Atlas was different. When Rahatgaonkar and his team analyzed the spectra from the Very Large Telescope, they found 22 distinct emission lines from neutral nickel atoms. The metal was there, unmistakable, fluorescing under solar radiation at a distance of nearly 4 times the Earth-Sun separation. Iron, however, was absent. Not just reduced, not just diminished, absent, below the detection limit. The nickel-to-iron ratio in 3I/Atlas was effectively infinite. In some observations, it exceeded 100 to 1. For comparison, the typical cometary ratio is roughly 1 to 1, despite the cosmic abundance favoring iron by nearly 20 to 1. The researchers published their findings in the Astrophysical journal Letters. The title was measured, as scientific papers tend to be, but the implications were anything but. Nickel without iron is not something that happens naturally. Not in comets, not in asteroids, not in meteorites, not anywhere in the cosmos where normal chemistry operates. There is, however, one place where pure nickel exists without iron contamination. One process that separates these cosmic siblings with ruthless efficiency. That process is called the Mond process, and it was invented by humans. In 1890, a German-born British chemist named Ludwig Mond was investigating a peculiar problem. Nickel valves in industrial equipment were corroding far faster than they should have been. When Mond traced the cause, he discovered something unexpected. At relatively low temperatures, around 50 to 60 degrees Celsius, nickel reacts with carbon monoxide to form a colorless, volatile liquid. He had accidentally synthesized nickel tetracarbonyl. This compound was unlike anything Mond had seen. Most nickel compounds are green solids. Nickel tetracarbonyl was a liquid that boiled at only 43 degrees Celsius and evaporated readily at room temperature. It was also extraordinarily toxic. But Mond recognized its potential immediately. The key insight was reversibility. Nickel tetracarbonyl forms at low temperatures, but when heated to around 200 degrees, it decomposes, depositing pure nickel metal and releasing carbon monoxide gas that can be recycled. This meant you could selectively extract nickel from a mixture of metals simply by exposing it to carbon monoxide, collecting the vapor, and heating it elsewhere. Iron could form a similar compound, iron pentacarbonyl, but there was a crucial difference. Iron pentacarbonyl is less volatile than nickel tetracarbonyl at the same temperature. Given the right conditions, you could vaporize the nickel while leaving the iron behind. By the end of the 19th century, Mond had commercialized this process for industrial nickel refining. The Mond process, as it came to be known, allowed the production of extremely pure nickel, over 99% purity, in a single step. It became the foundation of the modern nickel industry. The International Nickel Company, which dominated global nickel production for much of the 20th century, built its empire on Mond's discovery. Today, the Mond process remains one of the most efficient methods for separating nickel from other metals. It is used to produce high-purity nickel for electronics, batteries, and specialized alloys, and it is the only known natural or industrial process capable of producing nickel without detectable iron. When Harvard astrophysicist Avi Loeb learned about the spectroscopic results from 3I/Atlas, he did not mince words. The detection of nickel without iron, he wrote, is only known to exist in industrially produced alloys made through the artificial carbonyl chemical pathway. Most scientists dismissed this statement as sensationalism. Loeb has a history of provocative claims about interstellar objects, including his suggestion that the first such visitor, Oumuamua, might have been an alien light sail. His willingness to entertain extraterrestrial explanations where natural ones suffice has made him a polarizing figure in the astronomical community. But the underlying chemistry is not wrong. Nickel without iron is genuinely anomalous. Whether the explanation involves alien factories or exotic natural processes, 3I/Atlas was carrying a signature that demanded explanation. To understand the magnitude of this discovery, we need to step back and consider the history of interstellar objects. For most of human history, we had no idea they existed, or rather, we had no way to detect them. Objects moving through the solar system at hyperbolic velocities are rare and fast. They appear without warning, brighten briefly as they approach the sun, and vanish into the darkness before we can fully study them. Without the all-sky surveys that became operational in the 21st century, we simply could not find them. The theoretical prediction was clear. Planetary formation is a messy process. As planets grow, they gravitationally scatter smaller bodies in all directions. Some fall into the star, some crash into other planets, some settle into stable orbits in asteroid belts or comet clouds, and some are ejected entirely, launched into interstellar space at velocities that will carry them between the stars forever. If this happens in our solar system, it must happen elsewhere. Every star with planets must contribute to a vast population of interstellar debris, objects that outnumber the stars themselves, drifting through the galaxy on trajectories that occasionally bring them close to other suns. Models suggested that interstellar objects should pass through our solar system regularly, not frequently enough to notice without careful monitoring, but often enough that a sufficiently sensitive survey should detect one every few years. The arrival of 3I/Atlas, the third such object in less than 8 years, is consistent with these predictions. The first interstellar object was discovered on October 19, 2017, by the Pan-STARRS telescope in Hawaii. It was given the Hawaiian name Oumuamua, meaning a messenger from afar arriving first. The name was prescient. Oumuamua was indeed a messenger, but its message proved difficult to interpret. Oumuamua was strange from the start. It showed no coma, no tail, no visible outgassing. By the standard criteria, it was not a comet but an asteroid. Yet asteroids should not exist in interstellar space. The standard model of planetary formation predicts that icy comets are far more likely to be ejected than rocky asteroids, because comets form farther from their stars and are more easily disturbed by gravitational interactions. Even stranger, Oumuamua showed non-gravitational acceleration. As it passed through the solar system, it was being pushed by something other than gravity. For a comet, this would be normal. Outgassing acts like a rocket thruster, nudging the comet away from the sun. But Oumuamua showed no visible outgassing. Various explanations were proposed. Perhaps Oumuamua was made of hydrogen ice, which would sublimate invisibly. Perhaps it was a fragment of a larger comet that had lost most of its volatiles during a previous close encounter with a star. Perhaps, Loeb suggested, it was an artificial light sail, pushed by solar radiation pressure. The truth is, we do not know what Oumuamua was. It passed through too quickly, and it was too faint for detailed spectroscopic study. By the time we realized how unusual it was already receding into the outer solar system, dimming below the detection threshold of even our most powerful telescopes. 2I/Borisov, discovered in August 2019 by amateur astronomer Gennady Borisov, was more cooperative. It was clearly a comet, surrounded by a coma of gas and dust, displaying all the classic signatures of cometary activity. Spectroscopic observations detected water, carbon monoxide, hydrogen cyanide, and other familiar molecules. The chemical composition, while not identical to solar system comets, was broadly similar. Carbon monoxide was unusually abundant, but not inexplicably so. In 2021, researchers using the Very Large Telescope detected nickel vapor in Borisov's Comet. This was the first detection of a heavy metal in an interstellar object's atmosphere. Iron was also detected. The nickel-to-iron ratio was elevated compared to cosmic abundances, but similar to what had been observed in solar system comets. Borisov was reassuring in other ways too. Its trajectory was clearly hyperbolic, but its behavior was otherwise ordinary. It brightened as it approached perihelion, developed a dust tail, showed the spectral signatures we expect from comets. If you had not known it came from another star, you might have mistaken it for a particularly active Oort cloud comet, making its first close approach to the Sun. The contrast with Oumuamua was striking. One interstellar object was bizarrely inactive, perhaps depleted, perhaps something other than a comet entirely. The other was almost aggressively normal, doing everything a textbook comet should do. Together, they suggested that interstellar objects might span a wide range of types and compositions, just as solar system comets do. This diversity is what makes each interstellar visitor valuable. They are not all the same. They carry different chemical memories from different parent systems. The more we observe, the better we understand the full range of possibilities. The message from Borisov seemed to be reassuring. Comets are comets, wherever they form. The basic chemistry of icy bodies is universal, a product of the same processes that operate throughout the galaxy. 3I/Atlas challenged that conclusion. To understand the leading natural hypothesis, you need to understand what happens when a comet gets close to a star. As 3I/Atlas fell toward our Sun, its surface temperature began to rise. The first ices to respond were the most volatile, the compounds with the lowest sublimation points. Carbon dioxide, which makes up dry ice, transitions from solid to gas at temperatures around -78 Celsius at atmospheric pressure. In the vacuum of space, it can sublimate at even lower temperatures. When the James Webb Space Telescope trained its infrared sensors on 3I/Atlas in August of 2025, it found something remarkable. The coma surrounding the comet, the fuzzy cloud of gas and dust, was dominated by carbon dioxide. The ratio of carbon dioxide to water was roughly 8:1, among the highest ever recorded in any comet. For comparison, most solar system comets have carbon dioxide to water ratios of less than 1:1. This extreme composition suggested that 3I/Atlas had spent most of its existence in extraordinarily cold conditions, far colder than the outer reaches of our own solar system. It had preserved its volatile ices through billions of years of interstellar travel, and now those ices were awakening. The Webb observations revealed other peculiarities. Water ice was present, but in an unusual form. The spectral signature suggested very fine or amorphous ice grains, a texture rarely seen in solar system comets. Carbon monoxide was detected, along with carbonyl sulfide, a molecule containing carbon, oxygen, and sulfur. The carbon isotope ratio, comparing carbon-12 to carbon-13, was broadly similar to what we see on Earth and in our solar system. This was actually reassuring. Carbon isotope ratios are set by nuclear processes in stars, and the similarity suggested that 3I/Atlas formed in an environment with similar stellar chemistry to our own. At least some things were universal. But the outgassing pattern was strange. The carbon dioxide was being released preferentially in the direction of the Sun, forming an asymmetric coma that bulged toward our star rather than away from it. This anti-sunward jet, as it came to be called, defied the usual expectation that cometary outgassing should be driven by solar heating and thus strongest on the sunward side. Some scientists proposed that the jet was actually a standard cometary feature, viewed from an unusual angle, a trick of geometry rather than physics. Others suggested it might indicate unusual internal structure, with carbon dioxide ice buried beneath a less volatile surface layer. The debate continued, even as new anomalies emerged. But the carbon dioxide alone could not explain the nickel. The spectroscopic observations showed that nickel production increased dramatically as 3I/Atlas approached the Sun. At a distance of 3.8 astronomical units, roughly 3.8 times the Earth-Sun distance, the comet was producing approximately 4 grams of nickel per second. As it drew closer, this rate climbed by a factor of 25 in just 1 month. The increase followed a power law relationship with distance. The closer the comet got to the Sun, the more nickel it released, and the relationship was steeper than for any other comet ever observed. This was not simple sublimation of metal-rich dust. Something more complex was happening. The leading hypothesis involves organometallic chemistry. If nickel atoms are bound to carbon monoxide molecules, forming nickel tetracarbonyl, they can be released at relatively low temperatures. When ultraviolet sunlight strikes these molecules, they photodissociate, breaking apart into free nickel atoms and carbon monoxide gas. This would explain why nickel is detected without iron. Nickel tetracarbonyl is more volatile than iron pentacarbonyl, meaning it vaporizes at lower temperatures. At the distances where 3I/Atlas was observed, the conditions might be right for nickel carbonyl to sublimate. While iron carbonyl remains locked in the ice, the temperature differential is key. At 3.8 astronomical units from the Sun, where 3I/Atlas was when nickel was first detected, the equilibrium temperature is roughly 120 to 150 Kelvin. Nickel tetracarbonyl has a boiling point of 43 degrees Celsius at atmospheric pressure. But in the vacuum of space, sublimation can occur at far lower temperatures. Iron pentacarbonyl requires slightly higher temperatures to volatilize efficiently. This difference could create a window where nickel is released, but iron is not. As the comet warms further, iron should eventually appear. And indeed, this is what the observations showed. When 3I/Atlas crossed inside 2.6 astronomical units, iron emission finally became detectable. The nickel-to-iron ratio dropped from infinity to something merely extreme. But this explanation has problems. Nickel tetracarbonyl has a tetrahedral molecular structure with relatively strong nickel-carbon bonds. While it is more reactive than some organometallic compounds, it is not trivially broken apart by sunlight. The photodissociation mechanism requires specific ultraviolet wavelengths and may not be efficient enough to produce the observed nickel yields. Some calculations suggest that the energy required to break these bonds is too high for the solar radiation at the distances involved. The Keck Observatory in Hawaii observed 3 I/Atlas with its cosmic Webb imager, an instrument designed for extremely sensitive spectroscopy. The team, led by Willem Hugendam, detected nickel emission concentrated within about 600 kilometers of the nucleus. This tight spatial distribution suggested a parent molecule with a very short lifetime, breaking apart almost immediately after sublimation. Nickel tetracarbonyl fits this profile, but barely. The photodissociation rate in the solar radiation field at 3.8 astronomical units should produce a parent molecule lifetime of a few hundred seconds. The observations were consistent with this, but the uncertainties were large. More troubling is the question of how nickel tetracarbonyl would form in the first place. On Earth, the Mond process requires purified nickel metal in controlled conditions. In a comet, nickel exists primarily in sulfide minerals and silicate grains, not as pure metal. The formation of nickel carbonyl from these compounds would require chemical pathways that have not been documented in cometary environments. One possibility is that nickel carbonyl forms in the coma itself after nickel is released from grains by some other mechanism. The comet's carbon dioxide and carbon monoxide rich environment might provide the conditions for gas phase chemistry that would not occur in solar system comets with their water-dominated outgassing. Another possibility is that nickel carbonyl is primordial, incorporated into the comet during its formation. This would require unusual conditions in the alien protoplanetary disk, perhaps regions with high carbon monoxide abundance and temperatures in the narrow range where carbonyl formation is favored. Alternative hypotheses exist. Nickel might be bound to polycyclic aromatic hydrocarbons or fullerene molecules, which could release metal atoms when fragmented by ultraviolet light. Photon-stimulated desorption might eject nickel atoms directly from grain surfaces. The comet might contain nanophase nickel-rich materials with unusual volatility. All of these mechanisms are speculative. None have been confirmed in laboratory experiments or observed in solar system comets. 3. I/Atlas is forcing scientists to confront the possibility that cometary chemistry is far stranger than they assumed. Darrell Seligman led the first scientific paper published about 3 I/Atlas. An assistant professor at Michigan State University, Seligman had previously worked on the anomalous acceleration of Oumuamua and had become one of the world's leading experts on interstellar objects. When asked about the alien spacecraft hypothesis, he was diplomatic but firm. Almost everybody in the field is in agreement that this object is a natural comet because it is displaying classical evidence of cometary activity. He told reporters, "There is no controversy about it not being a comet because nobody thinks that except a very few people. The evidence supporting the natural comet interpretation is substantial." 3. I/Atlas has a visible coma. It has a tail. Spectroscopic observations have detected water ice, carbon dioxide gas, carbon monoxide, and hydrogen cyanide, all standard cometary constituents. Its brightness increases as it approaches the sun, following power laws consistent with ice sublimation. Its non-gravitational acceleration, caused by outgassing acting like a rocket thruster, is within the range observed for small solar system comets. None of these observations require an artificial explanation. The nickel anomaly is strange, but strangeness is not evidence of technology. It is evidence that we do not yet understand all the chemistry happening in interstellar space. This is a crucial point that often gets lost in the public discourse. Science does not prove things. It builds models that explain observations, and those models are always provisional, always subject to revision when new data arrives. The detection of nickel without iron in 3 I/Atlas does not prove that the object is artificial. It proves that our existing models of cometary chemistry are incomplete. That incompleteness is not a failure, it is an opportunity. Every scientific mystery begins with an observation that does not fit. Anomalies are the raw material of discovery. When spectroscopic observations of the Sun revealed unknown absorption lines in the 19th century, astronomers initially assumed they were seeing a new element, which they named helium after the Greek god of the Sun. They were right. Helium was later discovered on Earth, but the Sun had revealed it first. When the orbit of Mercury refused to match the predictions of Newtonian gravity, astronomers proposed a hidden planet, Vulcan, that might be perturbing its motion. They were wrong. The anomaly was eventually explained by Einstein's general relativity, a complete revision of our understanding of gravity. Anomalies can point to new physics, new chemistry, or simply to errors in our measurements. The scientific method cannot tell us in advance which category a particular anomaly belongs to. All it can do is provide a framework for testing hypotheses and refining our understanding. The nickel anomaly in 3 I/Atlas is currently unexplained. The carbonyl hypothesis is plausible but incomplete. The heterogeneous composition hypothesis is testable but untested. The artificial origin hypothesis is, in the judgment of most scientists, extremely unlikely but not strictly falsifiable with current data. Over the coming years, as the observations are analyzed and the models are refined, one or more of these hypotheses will emerge as the best explanation. The scientific consensus will shift, as it always does, toward the interpretation that best fits the evidence. This is how science works, not through sudden revelations or dramatic confrontations, but through the slow accumulation of evidence, the gradual elimination of alternatives, the patient refinement of models until they match what we observe. The process is messy and contentious and often frustrating, but it is the only reliable method humanity has ever devised for understanding the natural world. The nickel anomaly will yield to this process eventually. Maybe the carbonyl hypothesis will be confirmed, with laboratory experiments demonstrating that the required chemistry can occur under realistic cometary conditions. Maybe new observations of future interstellar objects will reveal similar signatures, establishing a pattern that natural explanations can account for. Maybe some entirely new mechanism will be proposed, one that no one has yet imagined, that explains the data more elegantly than anything currently on the table. Or maybe the anomaly will persist. Maybe 3 I/Atlas will remain for decades or centuries, an object whose chemistry we cannot fully explain. This would not be a failure of science. It would simply mean that some questions take longer to answer than others. The history of astronomy is full of phenomena that were observed long before they were understood. The nature of stars, the composition of nebulae, the source of the sun's energy. All of these were mysteries for generations before the necessary physics and chemistry were developed to explain them. 3I/Atlas might be such a mystery, a puzzle that our grandchildren will still be working on, a reminder that the universe does not operate on human timescales. The story of nickel in comets is itself remarkably recent. Until 2021, the conventional wisdom held that metallic elements like nickel and iron could only exist as vapor in extremely hot environments. When comet Ikeya-Seki grazed the Sun in 1965, passing within 1.5 solar radii of the photosphere, spectroscopic observations revealed emission lines from iron, nickel, copper, and other metals. This made sense. The comet's surface temperature had risen high enough to vaporize refractory minerals directly. The sun grazer comets were anomalies themselves, in a sense. They pass so close to the sun that their surfaces experience temperatures of thousands of degrees, far above the sublimation points of rock and metal. They are natural experiments in extreme heating, revealing what happens when a frozen body encounters conditions that should destroy it. Ikeya-Seki survived its close encounter, emerging from perihelion intact but dramatically altered. Its metal emissions faded as it retreated from the sun, the vapor cooling and condensing back into solid grains. By the time it reached the outer solar system, it looked like an ordinary comet again, its brush with destruction visible only in the memories of those who had watched. But cold comets, those observed at distances beyond 2 astronomical units from the sun, were not expected to show metallic emission. The temperatures were simply too low. Nickel and iron should remain locked in sulfide and silicate minerals, unreachable by the gentle warming that drives water and carbon dioxide sublimation. Then a team led by Jean Monfroy at the University of Liège made an unexpected discovery. Analyzing archival spectra from the Very Large Telescope, they found faint nickel and iron emission lines in more than 20 solar system comets observed over 2 decades of observations. The comets were far from the sun, some beyond 3 astronomical units, at temperatures well below the sublimation point of any known nickel or iron mineral. The detection was subtle. The emission lines were weak, easily overlooked in spectra dominated by far brighter features from water, carbon monoxide, and cyanide. Manfroy and his colleagues had been collecting spectra for other purposes and only realized the significance of the metal lines when they systematically reviewed their archive. The finding was published in Nature in May 2021. In the same issue, a separate paper by Piotr Guzik and Michał Draus reported the detection of nickel vapor in the coma of 2I/Borisov, the second interstellar object ever observed and the first confirmed interstellar comet. The detection was made at a heliocentric distance of 2.3 astronomical units, equivalent to an equilibrium temperature of about 180 Kelvin. The timing was either a remarkable coincidence or an example of how scientific discoveries sometimes cluster when the necessary tools become available. Both teams had been using the same instrument, the Very Large Telescope's high-resolution spectrograph, which was capable of resolving the weak nickel emission lines that other instruments might miss. Both papers proposed similar explanations. The nickel and iron must be bound in volatile organometallic compounds, most likely carbonyls, that can sublimate at low temperatures. When these compounds enter the coma and are exposed to solar ultraviolet radiation, they photodissociate, releasing free metal atoms. The carbonyl hypothesis explained the data, but it raised new questions. How did these compounds form? Were they primordial, incorporated into comets during their formation in protoplanetary disks, or did they form later, through chemical processing during the comet's long journey through space? Carbonyls are not common in nature. On Earth, they are primarily industrial chemicals produced in laboratories and factories for specific applications. The idea that they might exist naturally in comets was surprising. To understand why the connection to industry raised eyebrows, you need to know the history of how humans learned to work with nickel carbonyls. In 1890, a German-born British chemist named Ludwig Mond made a discovery that would transform industrial metallurgy. Mond was already wealthy and famous for his contributions to the alkali industry, having developed improved methods for producing sodium carbonate. He had turned his attention to nickel, a metal that was difficult to purify using existing techniques. The conventional methods for extracting nickel from ore involved roasting, smelting, and electrolysis, all of which were energy-intensive, slow, and produced metal of variable purity. Mond was looking for something better. The breakthrough came when Mond and his assistants noticed that carbon monoxide gas, which they were using in their laboratory for other experiments, seemed to react with nickel. When they passed carbon monoxide over finely divided nickel metal at around 50 degrees Celsius, the metal seemed to disappear, converting into a gas. Further investigation revealed that nickel was combining with carbon monoxide to form nickel tetracarbonyl, a colorless liquid with a boiling point of 43 degrees Celsius. The reaction was remarkably clean. 4 molecules of carbon monoxide attached to each nickel atom, forming a tetrahedral structure that was volatile enough to evaporate at barely above room temperature. The reverse reaction was equally important. When nickel tetracarbonyl was heated to around 180 degrees Celsius, it decomposed, releasing pure nickel metal and regenerating carbon monoxide. The carbon monoxide could be recycled and used to process more ore. Mond had discovered a way to purify nickel that was elegant, efficient, and scalable. The process, which came to be known as the Mond process, could produce nickel of 99.9% purity, far exceeding what conventional methods could achieve. The Mond Nickel Company, founded to exploit this discovery, became one of the largest nickel producers in the world. The process is still used today, more than a century after its invention. The nickel that coats your coins, the nickel in stainless steel alloys, the nickel in rechargeable batteries may have been purified using the chemistry that Ludwig Mond discovered. Iron also forms carbonyls, but the chemistry is different. Iron pentacarbonyl requires higher temperatures to form and higher temperatures to decompose. The process is less efficient for iron than for nickel. This is why the Mond process is primarily used for nickel and not for iron. The different volatilities of nickel and iron carbonyls create a natural separation. If you have a mixture of nickel and iron, and you pass carbon monoxide over it at the right temperature, the nickel will preferentially convert to carbonyl and evaporate, leaving the iron behind. This is effectively what the Comet observations suggest is happening in 3I/Atlas, but at temperatures far below anything Ludwig Mond worked with. When the public learned that 3I/Atlas Atlas was showing nickel without iron, and that the only known process capable of achieving such separation was an industrial technique. The implication was hard to miss. Had someone built this comet? Had some alien civilization processed nickel ore using the same chemistry that Ludwig Mond discovered, and then launched the purified material into interstellar space? The suggestion was tantalizing, but it faces severe problems. First, the nickel in 3I/Atlas is not pure. It is embedded in a matrix of water ice, carbon dioxide ice, and various organic compounds. If someone wanted to send refined nickel between the stars, packing it in dirty ice would be a strange way to do it. Second, the quantities involved are minuscule. The comet is producing a few grams of nickel per second, which sounds like a lot until you realize that the total amount released during its passage through the inner solar system amounts to perhaps a few hundred kilograms. Any civilization capable of interstellar travel could produce more nickel than that in a single afternoon. Third, and most importantly, the carbonyl mechanism can explain the observations without invoking technology. If nickel tetracarbonyl is present in the comet naturally, either incorporated during formation or produced by chemical processing during its interstellar voyage, then the same separation that the Mond process achieves industrially could occur spontaneously as the comet warms. The coincidence is remarkable, but not impossible. Chemistry operates according to universal laws. The same reactions that Ludwig Mond exploited in his laboratory can occur naturally, given the right conditions. The comet does not need a factory. It just needs carbon monoxide and nickel in close proximity, with enough thermal energy to drive the reaction. But the evidence was clear. Nickel and iron were present in cold cometary atmospheres where they had no business being. Some volatile carrier was transporting them from the solid nucleus into the gaseous coma. Carbonyls were the most plausible candidates. In solar system comets, the nickel-to-iron ratio in the coma is roughly 1:1, despite iron being about 18 times more abundant in the cosmic average. This suggests that nickel carbonyl is preferentially released over iron carbonyl, consistent with its higher volatility. But the effect is modest. Both metals are present. 2I/Borisov showed a similar pattern. Nickel and iron were both detected, with an abundance ratio comparable to solar system comets. 3I/Atlas broke the pattern completely. There is another possibility that scientists are reluctant to discuss publicly, but cannot entirely rule out. What if 3I/Atlas is not a single homogeneous object? Comets are not uniform spheres of ice. They are irregular, lumpy conglomerations of material that accumulated over millions of years in a protoplanetary disk. Different regions of a comet can have different compositions, reflecting different conditions in different parts of the disk where they formed. When a comet becomes active, the ices that sublimate may come from localized pockets rather than from the entire surface uniformly. The Rosetta mission to Comet 67P/Churyumov-Gerasimenko revealed just how varied cometary structure can be. The comet had two distinct lobes, likely the result of a gentle collision between two separate bodies early in the solar system's history. Different regions showed different ice compositions, different dust properties, different levels of activity. What looked like a single object was actually a complex assemblage of materials with different origins. If 3I/Atlas contains isolated deposits of nickel-rich material, perhaps concentrated by some unknown process during its formation or subsequent evolution, the observed emission might represent outgassing from these specific regions. Iron-rich material might exist elsewhere on the comet, but not be currently exposed to solar heating. The comet is rotating with a period of about 16 hours. As it spins, different parts of its surface cycle between sunlight and shadow. If nickel-rich deposits are concentrated in regions that have been preferentially illuminated during the observing campaign, we might see enhanced nickel emission without corresponding iron. This hypothesis is testable, at least in principle, as 3I/Atlas moves through the solar system. Different parts of its surface are illuminated by the sun at different times. If the nickel-to-iron ratio changes significantly as the comet rotates or as different hemispheres become active, that would support the heterogeneous composition model. Some observations suggest this might be happening. In the early phases of 3I/Atlas's approach, iron was completely undetected. But as the comet drew closer to the sun, crossing within 2.6 astronomical units, iron emission finally appeared. The nickel-to-iron ratio dropped from effectively infinite to something merely extreme, still far higher than solar system comets, but no longer zero. This evolution is consistent with the carbonyl hypothesis. Nickel tetracarbonyl sublimates at lower temperatures than iron pentacarbonyl. So as the comet warms, iron begins to appear. Eventually, when surface temperatures rise high enough, both metals should be released in proportion to their actual abundances, but it could also be consistent with heterogeneous composition. As the comet approaches the sun, heat penetrates deeper into its interior, activating regions that were dormant at larger distances. If iron-rich deposits are buried beneath nickel-rich surface layers, we would expect iron to appear later as heating intensifies. The observations cannot currently distinguish between these scenarios. Both predict that iron should increase relative to nickel as the comet warms. Both predict that the extreme ratios observed early on should moderate over time. To truly test the heterogeneous composition hypothesis, we would need spatially resolved spectroscopy of the comet's coma, mapping where the nickel and iron are coming from at different times. Such observations are at the limit of current technology. The question is whether the ratio will normalize completely. As of late 2025, 3I/Atlas had passed perihelion and was heading back out toward the cold. The window for observing its most active phase had closed. The comet had dipped behind the sun from Earth's perspective during the critical days around perihelion, blocking ground-based observations at precisely the moment its activity peaked. But space-based assets were watching. NASA had mobilized an unprecedented effort to track 3I/Atlas. The Hubble Space Telescope captured high-resolution images of its coma and nucleus. The James Webb Space Telescope analyzed its infrared spectrum. The Mars orbiters, including Mars Reconnaissance Orbiter, ExoMars Trace Gas Orbiter, and MAVEN, turned their cameras toward the comet as it passed relatively close to the red planet in early October. The coordination was remarkable. NASA's Planetary Defense Coordination Office added 3I/Atlas to the International Asteroid Warning Network's observation campaign, not because the comet posed any threat, but because the network's protocols provided a framework for coordinating global observations. Between November and late January, telescopes around the world focused on refining the comet's trajectory and monitoring its behavior. Each spacecraft brought unique capabilities. Mars Express and the ExoMars Trace Gas Orbiter had the closest views of any ESA spacecraft, catching the comet as it passed within 30 million kilometers of Mars in early October. The images showed a fuzzy coma, clearly visible despite the enormous distance. The Europa Clipper spacecraft, en route to Jupiter's icy moon, was predicted to pass through the comet's ion tail between late October and early November. If successful, this would provide direct sampling of material released from an interstellar object, a first in human history. The spacecraft's instruments were designed to study Europa's thin atmosphere, but they could potentially detect ions and charged particles from 3I/Atlas's outgassing. NASA's Lucy mission, heading toward the Trojan asteroids, spotted the comet from about 240 million miles away. The Psyche spacecraft, bound for a metallic asteroid, captured 4 observations over 8 hours. Even solar observatories got involved. The Stereo mission, designed to study the Sun, imaged 3I/Atlas as a short elongation in colorized, stacked images. The SOHO coronagraph caught a glimpse of the comet near perihelion. The MAVEN orbiter at Mars used its ultraviolet instruments to image the hydrogen atoms surrounding the comet, revealing the extent of its gaseous envelope. The Perseverance and Curiosity rovers on the Martian surface attempted to photograph the comet, adding ground-based observations from another planet to the dataset. Even the Voyager spacecraft, now in interstellar space themselves, served as a poignant reminder. They are our contributions to the population of objects drifting between the stars, tiny compared to 3I/Atlas, but carrying the unmistakable signature of technological origin. The data from these missions will take months or years to fully analyze, but early results confirmed what ground-based observations had already suggested. 3I/Atlas is genuinely unusual. Its chemistry differs not only from solar system comets, but also from the previous interstellar comet, 2I/Borisov. That difference is itself significant. If interstellar comets were all alike, their compositions reflecting some universal process of comet formation around all stars, they would not teach us very much. The diversity of 3I/Atlas compared to 2I/Borisov suggests that different star systems produce different kinds of comets with different chemical signatures, preserving different records of their formation environments. This is actually the outcome scientists hoped for, even if the specific differences are puzzling. Each interstellar object is a time capsule from another world. The more they differ from each other and from our own solar system's comets, the more they reveal about the range of conditions that exist across the galaxy. The study of planetary formation has undergone a revolution in recent decades. When the first exoplanet around a sun-like star was discovered in 1995, astronomers expected to find systems that resembled our own. They expected to find small rocky planets close to their stars, gas giants at moderate distances, ice giants further out, and debris disks of asteroids and comets populating the gaps. What they found instead was chaos. Hot Jupiters orbiting closer to their stars than Mercury orbits the Sun, super-Earths with no analog in our solar system. Planets larger than Earth but smaller than Neptune, more common than any other type. Planetary systems packed so tightly that neighboring worlds could appear larger than the full moon in each other's skies. Systems with wildly eccentric orbits, planets swinging from near their stars to the outer reaches and back again. The diversity was humbling. Our solar system, with its orderly arrangement of planets in nearly circular orbits, turned out to be atypical. The universe was far messier, far more creative than our local example had suggested. But exoplanet observations have limitations. They tell us about the planets themselves, their sizes, masses, orbits, and sometimes their atmospheric compositions. They tell us very little about the small bodies, the asteroids and comets that orbit in the spaces between planets. These objects are too small and too faint to detect around other stars with current technology. Interstellar objects change that. When a comet from another star system passes through our own, we can study it up close. We can analyze its spectrum, measure its outgassing, determine its composition with a precision that would be impossible for any object remaining in its home system. We can learn what the building blocks of that distant planetary system were made of, how they formed, and what conditions prevailed in the protoplanetary disk billions of years ago. 3I/Atlas is a window into another world's history. Its extreme carbon dioxide content suggests formation in conditions colder than anything in our solar system's comet-forming region. Its nickel anomaly suggests chemistry that we do not yet understand. Its high velocity and long travel time suggest origins in a star system that was already ancient when our sun had not yet ignited. Every measurement is a clue. Every chemical species is a message from the past. The comet has been carrying this information for billions of years, frozen and inert in the cold between the stars, waiting for some sun to warm it, some world to notice it, some intelligence to wonder what it means. We happened to be here when it arrived. We happened to have the tools to study it. We happened to ask the right questions. That is not coincidence. That is the result of centuries of scientific progress, of telescope building and spectrum analysis and theoretical modeling. We prepared ourselves, without knowing it, to receive this visitor. The questions we ask of 3I/Atlas are questions we have been asking of our own solar system for generations. Now we can extend them to the galaxy. The nickel anomaly is strange and unexplained, but it is not the most important thing about 3I/Atlas. The most important thing is that it exists, that objects from other solar systems pass through our own with some regularity, that the galaxy is not a collection of isolated islands, but a sea through which materials flow, carrying chemical memories of their origins across unfathomable distances. We are just beginning to explore that sea. Consider what 3I/Atlas's composition tells us, setting aside the nickel question for a moment. The extreme carbon dioxide to water ratio suggests formation in a very cold region, probably beyond the carbon dioxide ice line, where temperatures were cold enough for dry ice to freeze, but not necessarily cold enough for water ice to accumulate efficiently in our own solar system. This would correspond to the outer reaches of the Kuiper belt or the inner Oort cloud, but conditions vary from star to star, and the exact location of ice lines depends on the luminosity and mass of the central star. The high velocity of 3I/Atlas, 58 kilometers per second, suggests it was ejected from its home system by a strong gravitational encounter. This typically happens when a small body passes close to a giant planet, receiving a gravitational kick that boosts it above escape velocity. The faster the ejection, generally, the closer the encounter. In our own solar system, Jupiter is the primary ejector. Its massive gravity slings comets and asteroids out of the solar system regularly. Saturn, Uranus, and Neptune contribute as well, but to a lesser degree. If 3I/Atlas was ejected by a similar process, its home system likely contained at least one giant planet. The age estimate of 3 to 11 billion years places the comet's birth in an earlier epoch of galactic history. Stars that formed 7 or more billion years ago had, on average, lower metallicity than the Sun. Metallicity, in astronomical parlance, refers to the abundance of elements heavier than helium. These elements are produced by stars and dispersed into space when stars die. Over cosmic time, as generations of stars have lived and died, the galaxy's metallicity has gradually increased. A comet from a low metallicity star might have different proportions of heavy elements than one from our solar system. Iron and nickel are both products of stellar nucleosynthesis, created in the cores of massive stars and dispersed by supernova explosions. The relative abundance of these elements could vary depending on the specific history of the star and its progenitors. But this does not obviously explain the nickel anomaly. Lower overall metallicity would affect both nickel and iron similarly. It would not produce a comet where nickel is abundant and iron is undetectable. Something else is going on. 3I/Atlas might have formed close to its parent star's carbon dioxide ice line, where temperatures were cold enough for dry ice to freeze, but not cold enough for water ice to be abundant. That would explain its high carbon dioxide to water ratio. It might have been exposed to unusually high levels of ultraviolet radiation, either from its parent star or from the interstellar medium during its long voyage, altering its surface chemistry in ways we do not yet understand. Or it might have formed around a metal-poor star, one with unusual elemental abundances that favored nickel-bearing compounds over iron-bearing ones. Each of these hypotheses makes predictions that can be tested with additional observations. Each tells us something about the diversity of planetary systems across the galaxy. Each reminds us that the cosmos is stranger and more varied than our parochial experience of one solar system would suggest. On December 19th, 2025, 3I/Atlas made its closest approach to Earth. The distance was still enormous by terrestrial standards, about 168 million miles, roughly 1.8 astronomical units. The comet was never visible to the naked eye, but for those who knew where to look, with binoculars or small telescopes, it appeared as a faint, fuzzy smudge in the constellation Lepus, just south of Orion. By then, the object had captured the public imagination in ways that scientific papers rarely do. Part of this was timing. 3I/Atlas arrived during a period of heightened public interest in space exploration and extraterrestrial life. The previous decade had seen the detection of thousands of exoplanets, including dozens in potentially habitable zones around their stars. The search for biosignatures in exoplanet atmospheres was advancing rapidly, and the first two interstellar objects, Oumuamua and 2I/Borisov, had already primed people to think about visitors from other star systems. The James Webb Space Telescope had transformed our understanding of distant galaxies and exoplanet atmospheres. The Perseverance rover was collecting samples on Mars that might someday be returned to Earth and searched for signs of ancient life. The public was primed for discovery, for contact, for something that would reshape our understanding of our place in the cosmos. Part of it was the nickel anomaly itself. The phrase nickel without iron had an almost alchemical quality, suggesting something uncanny, something that violated the natural order. When news outlets reported that the chemical signature had only been seen before in industrial refining processes, the implication was obvious, even if rarely stated explicitly. This comet might be artificial. Social media amplified the speculation. Analysis of roughly 700,000 posts about 3I/Atlas on the X platform found that nearly 40% mentioned aliens or extraterrestrial technology. The hashtag 3IAtlas trended repeatedly. YouTube videos with titles like "Is 3I/Atlas an alien spacecraft?" accumulated millions of views. The speculation reached a fever pitch in late October when Avi Loeb published a series of blog posts enumerating what he called the anomalies of 3I/Atlas. The comet's trajectory was aligned with the ecliptic plane of our solar system to within 5 degrees, a coincidence with only a 0.2% probability of occurring by chance. Its brightness had increased faster than expected as it approached perihelion. Its emission spectrum showed unexpected colors, and of course, there was the nickel. Loeb proposed a classification scale for interstellar objects, running from 0, confirmed natural, to 10, confirmed technological. He rated 3I/Atlas a 4, acknowledging that it was most likely a natural comet, while insisting that the technological possibility could not be dismissed. He went further, co-authoring a paper that explored what it would mean if 3I/Atlas were an alien spacecraft. The paper invoked the dark forest hypothesis, a scenario from science fiction where civilizations hide from each other because revealing your existence invites attack from hostile neighbors. If alien civilizations were sending probes to survey potentially habitable star systems, they might design them to look like natural objects, avoiding detection while gathering data. The paper was explicitly labeled as pedagogical, a thought experiment rather than a claim. But the distinction was lost on much of the public. Headlines announced that a Harvard scientist believed 3I/Atlas might be hostile alien technology. The mainstream astronomical community pushed back hard. Jason Wright, an astronomer at Penn State who studies exoplanets and the search for extraterrestrial intelligence, compiled a detailed rebuttal of Loeb's anomaly list. Each supposed anomaly, he argued, had a mundane explanation. The ecliptic alignment was not as improbable as claimed when selection effects were considered. The brightness increase was consistent with cometary activity at the observed heliocentric distances. The colors were unremarkable for a dusty comet. And the nickel. Wright acknowledged that the chemistry was unusual, but noted that unusual did not mean artificial. The carbonyl hypothesis provided a natural mechanism that was consistent with the observations. The fact that the Mond process produced similar results on Earth was a coincidence, not evidence of alien manufacturing. Science requires evidence proportional to claims, Wright wrote. Extraordinary claims require extraordinary evidence. 3I/Atlas, while interesting, has not provided evidence that requires an extraordinary explanation. Tom Statler, NASA's program scientist for 3 I/Atlas observations, was even more direct. The overwhelming evidence, he told reporters, suggests that 3 I/Atlas is a natural comet. It behaves like a comet. It looks like a comet. The unusual features we observe can be explained by the fact that it formed in a different solar system under different conditions. The scientific response to 3 I/Atlas was, in many ways, a model of how the astronomical community handles unusual objects. Within days of the discovery announcement, observers around the world were coordinating their efforts, dividing up the electromagnetic spectrum so that every wavelength would be covered. Radio telescopes searched for artificial signals, finding none. The Allen Telescope Array, the Greenbank Telescope, and the Very Large Array all conducted targeted observations. If 3 I/Atlas was broadcasting on any frequency that radio astronomers typically monitor, the signal would have been detected. The silence was not conclusive proof of natural origin, but it was consistent with it. Optical telescopes measured the comet's rotation period, finding it spinning once every 9 hours or so. The rotation was consistent with a natural body that had been tumbling through space for billions of years, slowly exchanging angular momentum with ejected material. An artificial probe might be expected to show more controlled motion, perhaps spin stabilization or attitude control corrections. Infrared observations constrained the comet's size and albedo. 3 I/Atlas was small, perhaps 2 to 3 kilometers in diameter, with a reflectivity typical of dark, carbonaceous material. Its surface was not metallic, not highly reflective, not composed of anything that looked engineered. The Hubble Space Telescope captured the highest resolution images available, revealing a fuzzy nucleus surrounded by a symmetric coma. There were no hard edges, no geometric features, no indication of anything other than a dirty snowball awakening in the warmth of an unfamiliar star. But the observations also revealed just how much we do not know. The asymmetric carbon dioxide outgassing remained unexplained. The extreme nickel-to-iron ratio had no clear analogue among solar system comets. The carbon dioxide to water ratio suggested formation conditions that do not exist in our planetary system. Each measurement added to the puzzle. The comet was natural, almost certainly, but it was also strange in ways that could not be attributed to observational error or selection effects, strange in ways that challenged our models of how comets form and evolve. The Very Large Telescope observations led by Rohan Rahatgaonkar and collaborators at Pontificia Universidad Católica de Chile detected 22 distinct nickel emission lines in the comet's spectrum. The forest of lines allowed precise measurements of nickel abundance, velocity, and distribution within the coma. No other comet had ever been characterized in such detail. The nickel was being produced at a rate that increased as the comet approached the Sun, following a relationship with heliocentric distance that was steeper than expected. The power law index was higher than for any previously observed comet, suggesting a source mechanism that was unusually sensitive to temperature. If the carbonyl hypothesis was correct, this steep dependence made sense. Nickel tetracarbonyl has a relatively sharp sublimation threshold. Below certain temperatures, it remains frozen. Above that threshold, it evaporates rapidly. The transition is more abrupt than for water ice or even carbon dioxide ice, which might explain the unusual brightness curve. But there were complications. The gas production rates implied by the nickel emission did not perfectly match the production rates implied by the carbon dioxide emission. Either the carbonyl hypothesis was incomplete, or there were multiple source mechanisms contributing to the observed metal abundances. Some researchers proposed that nickel might be released from organic matrices rather than carbonyl compounds. Complex organic molecules, heated by sunlight, could fragment and release metal atoms that had been chelated within their structures. This mechanism would not require the Mond process chemistry and could operate over a wider temperature range. Others suggested that photon-stimulated desorption from grain surfaces might be important. Ultraviolet photons striking dust grains could eject metal atoms directly, without requiring any volatile carrier molecule. This process is known to occur in laboratory experiments and might contribute to the metal content of the coma. The debate continues because the data, while extensive, are not definitive. 3 I/Atlas passed through the inner solar system in 6 months, barely enough time for the scientific community to mount a coordinated observation campaign, let alone resolve every question the object raised. This is the curse of interstellar objects. They arrive without warning, stay briefly, and depart forever. There is no opportunity to follow up, to request additional measurements, to test new hypotheses as they emerge. Whatever we learn about 3 I/Atlas, we had to learn during its single passage. The comet will not return to clarify our confusion. As 3 I/Atlas recedes into the outer solar system, bound for Jupiter and then the interstellar void beyond, the debate continues. Most scientists are confident that the object is natural, a comet, albeit a strange one, carrying the chemical memory of an alien solar system where conditions were different enough to produce unusual organometallic compounds. The nickel anomaly will eventually be explained by some combination of carbonyl chemistry, heterogeneous composition, and observational selection effects. The mystery will yield to ordinary science, but a minority remain intrigued by the questions that remain unanswered. Why is the nickel-to-iron ratio so extreme compared to both solar system comets and the previous interstellar comet? If the carbonyl hypothesis is correct, why have similar signatures not been observed in other carbon dioxide-rich comets? What specific conditions in an alien protoplanetary disk could produce such unusual chemistry? These questions matter regardless of the answer. If 3 I/Atlas is natural, understanding its composition will reveal new insights into the diversity of planetary systems across the galaxy. If, against all probability, it is artificial, the implications would be revolutionary. The honest answer is that we do not know. And that uncertainty, that gap between what we observe and what we understand, is the engine that drives science forward. In 1977, the Voyager spacecraft were launched from Cape Canaveral, carrying golden records inscribed with sounds and images from Earth. They were messages in a bottle, cast into the cosmic ocean on the slim chance that some distant intelligence might find them. The records contained greetings in 55 languages, music from Bach to Chuck Berry, natural sounds from thunder to whale songs. They carried photographs of Earth and its inhabitants, diagrams showing our location in the galaxy, instructions for playing the record itself. They were the most elaborate attempt humanity has ever made to communicate with extraterrestrial intelligence. 48 years later, both voyages are still traveling, now beyond the heliopause, in the interstellar medium. Voyager 1 is the most distant human-made object, more than 15 billion miles from the Sun. It takes over 22 hours for radio signals to reach it, traveling at the speed of light. The Voyagers are our first deliberate contributions to the population of objects drifting between the stars. Small and fragile compared to the icy mountains of comets, but carrying the unmistakable signature of technological origin. Their golden records will outlast human civilization, potentially surviving for billions of years in the cold vacuum of interstellar space. 3I/Atlas is not a Voyager. It is almost certainly a natural comet, a frozen relic of a planetary system that formed billions of years before our Sun ignited. Its nickel signature, however strange, will probably be explained by chemistry we do not yet fully understand. But the Voyagers remind us that technological objects do exist in interstellar space. Some were sent deliberately. Others, perhaps, were lost or discarded or abandoned. If even one civilization in the galaxy has sent probes to explore, over the billions of years since the first stars formed, there could be millions of such objects drifting through the void. Most would be dead, their power supplies exhausted, their electronics degraded by cosmic radiation, but they would still be there, tumbling silently through the darkness, carrying the signatures of their makers, even if their makers have long since vanished. We would not expect such probes to be common. The galaxy is vast, and even millions of probes would be scattered thinly across its hundreds of billions of star systems. The chance of one passing through our solar system while we happen to be watching is minuscule, but it is not zero. The future of interstellar object research is bright, whatever 3I/Atlas turns out to be. The Vera Rubin Observatory, currently commissioning in Chile, will transform our ability to detect these visitors. Its 8.4-meter primary mirror and 3.2 billion pixel camera will survey the entire visible sky every few nights, capturing images of objects far fainter than any previous survey could reach. Current estimates suggest that Rubin will discover interstellar objects at a rate of one or more per year, perhaps hundreds over its planned decade of operations. Each discovery will be an opportunity to study materials from another star system, an opportunity to test our models of cometary chemistry, an opportunity to search for signatures that might indicate technological origin. The European Space Agency is developing Comet Interceptor, a mission designed to wait in space for a suitable target. Launched into a parking orbit around the second Lagrange point, it will remain dormant until astronomers discover a pristine comet from the outer solar system, or potentially an interstellar object. When the right target appears, Comet Interceptor will be dispatched to intercept it, making the first close flyby of a truly pristine comet. An interstellar intercept would be the Holy Grail. Close-range observations could resolve questions that remain unanswerable from Earth: the shape of the nucleus, the distribution of active regions, the detailed composition of the coma, the presence or absence of unexpected features. If Comet Interceptor was sent to an interstellar object, it could potentially detect the carbonyl compounds directly, rather than inferring their presence from metal emission lines. It could measure the elemental abundances of the nucleus material. It could determine whether the nickel anomaly extends to the solid surface or is purely a coma phenomenon. The probability of an interstellar intercept is low. The objects are rare, and their trajectories are unpredictable. Comet Interceptor might spend its entire mission waiting for a target that never comes. But the potential payoff is enormous. A single interstellar rendezvous could answer questions that centuries of Earth-based observation cannot. Beyond Comet Interceptor, more ambitious concepts have been proposed. A dedicated interstellar object chaser, pre-positioned in space with enough propellant to reach any target that enters the inner solar system. A network of small spacecraft distributed throughout the solar system, ready to converge on any interstellar visitor. A sample return mission, capturing material from an interstellar comet and bringing it back to Earth for laboratory analysis. These missions are beyond current technology or funding, but they are not impossible. The scientific motivation is clear. The engineering challenges, while formidable, are solvable. If humanity decides that studying interstellar objects is a priority, we have the capability to do far more than we are doing now. 3I/Atlas is a wake-up call. It shows us what is possible when an interstellar visitor arrives and we are watching. It also shows us how much we cannot learn with current capabilities. The next interstellar object might be even stranger. The one after that might be unprecedented. We will never know unless we are ready to observe them, to analyze them, to visit them if we can. That possibility is why we look. Not because we expect to find aliens, but because we cannot afford to miss them if they exist. There is a deeper lesson in the story of 3I/Atlas, one that transcends the specific chemistry of nickel and iron. We live in a universe that constantly surprises us. Every time we build a new instrument, every time we extend our vision to a new wavelength or a new sensitivity, we discover something unexpected. The history of astronomy is a history of anomalies, of observations that did not fit existing models, of data that forced us to revise our understanding. Pulsars were discovered when radio astronomers found regularly pulsing signals that they initially nicknamed LGM for little green men. The cosmic microwave background was discovered when radio engineers found unexplained noise in their antenna that turned out to be the echo of the Big Bang. Dark matter was proposed when galaxy rotation curves refused to match the predictions of Newtonian gravity. None of these anomalies turned out to be alien signals. All of them turned out to be natural phenomena, far stranger and more interesting than alien technology would have been. Pulsars are rapidly spinning neutron stars, the collapsed cores of massive suns, packing more mass than the sun into a sphere the size of a city. The cosmic microwave background is the oldest light in the universe, emitted when the cosmos was less than 400,000 years old. Dark matter is a new form of matter that does not interact with light, invisible to all our instruments except through its gravitational effects. 3I/Atlas might follow the same pattern. The nickel anomaly might lead us to new chemistry, new physics, new understanding of how materials behave in the cold depths of interstellar space. It might reveal processes that operate in alien protoplanetary disks, conditions that do not exist in our solar system, but are common elsewhere in the galaxy. or it might not. Science does not guarantee insights. Sometimes anomalies turn out to be measurement errors or statistical fluctuations or artifacts of incomplete models. Sometimes the universe withholds its secrets despite our best efforts to pry them loose. But we cannot know in advance which anomalies will yield treasure and which will yield dust. The only way to find out is to investigate, to observe, to test, to refine our models until they either explain the data or collapse under the weight of their inadequacy. 3I/Atlas has given us that opportunity. A visitor from the stars, carrying chemistry we do not understand, challenging us to expand our knowledge or admit our ignorance. That is the gift. Not answers, but questions. Not certainty, but wonder. 3I/Atlas was discovered on a Tuesday. By Friday, 40 international observatories had trained their instruments on it. Within a month, the first peer-reviewed paper had been published. Within 3 months, every major space telescope had contributed observations. Within 6 months, the comet had passed perihelion and was on its way out of the solar system forever. This is the speed of modern astronomy. A visitor from another star arrives unannounced, and humanity responds with a coordinated global effort to learn everything we can before it vanishes. The nickel anomaly will be debated for years. Papers will be written, models will be refined, theories will be proposed and tested and discarded. Eventually, a consensus will emerge. The chemistry of 3I/Atlas will become another data point in our understanding of how planetary systems form and evolve across the galaxy. But something else will remain. The memory of those weeks in the summer and fall of 2025, when the world watched a messenger from the stars, carrying secrets written in frozen metal and ancient ice, when scientists set aside their other projects to chase an object that would never return. When the boundary between the known and the unknown, between our solar system and the vast galaxy beyond, became a little more porous. Every interstellar object is a reminder that we are not alone in the universe, not in the sense of aliens or spacecraft or messages from distant civilizations, but in the simpler, more profound sense that the same elements, the same chemistry, the same physics operate everywhere. That the nickel atoms in 3I/Atlas were forged in the same stellar processes that created the nickel in your body. That the carbon dioxide sublimating from its surface is the same molecule you exhale with every breath. We are made of the same stuff as this wanderer from the stars. Its story is, in some deep way, our story too. And when it leaves, carrying its mysteries back into the interstellar void, we will be left with the questions it provoked. Questions about chemistry and cosmology, about the formation of planets and the diversity of solar systems, about what is natural and what is possible. Those questions are the real gift of 3I/Atlas. They are the reason we build telescopes and train them on the faint smudges of light moving against the stars. They are the reason we do science at all. The comet will pass Jupiter in early 2026. By then, it will be too faint for most ground-based telescopes to observe. The Hubble and James Webb will track it a while longer, watching as its activity fades and its coma dissipates. Eventually, even they will lose sight of it. 3I/Atlas will continue outward, crossing the orbit of Saturn, then Uranus, then Neptune. By the end of the decade, it will be beyond the Kuiper Belt, entering the sparse outer reaches of the solar system. By mid-century, it will have left our gravitational influence entirely, resuming its journey through interstellar space. It will not return. In a few billion years, it might pass through another solar system. If that system has telescopes and scientists, they might detect it. They might wonder where it came from. They might analyze its spectrum and find evidence of nickel, perhaps still anomalously abundant compared to iron, a chemical signature preserved across unfathomable time and distance. They would not know about us, about the summer of 2025, when a small blue planet in an unremarkable solar system noticed their comet and spent 6 months trying to understand it. But they would know that someone, somewhere, had once asked the same questions they were asking. That is what interstellar objects do. They connect us across time and space to every other world that has ever wondered about the cosmos. And that connection, fragile and fleeting as it is, matters more than any answer. There is something almost sacred about watching an interstellar object pass through our solar system. For billions of years, 3I/Atlas traveled alone, to vast reaches of empty space, where the nearest stars were points of light barely brighter than the background glow of the Milky Way. Past molecular clouds and stellar nurseries, remnants of supernova, and the slow drift of dark matter, through regions where nothing happens for millions of years, where entropy creeps forward imperceptibly, where time itself seems to slow. And then, for a few brief months, it entered a sphere of activity, a solar system with planets and moons and spacecraft and telescopes and creatures capable of wondering what it was. We will never know how many solar systems 3I/Atlas has passed through before ours. The galaxy contains roughly 200 billion stars, and the comet has been traveling for at least 3 billion years. Depending on its trajectory, it might have passed within a few light years of hundreds of stars, close enough to feel their gravitational pull, close enough to appear as a faint point of light in their skies. But close encounters are different. The probability of passing within an astronomical unit of a random star, close enough to be heated and activated and observed, is vanishingly small. 3I/Atlas's passage through our solar system might be a once-in-a-lifetime event, not just for us, but for the comet itself. It might never again come close enough to a star to awaken from its frozen slumber. We caught it at a special moment, a moment when it was close enough to study, active enough to reveal its chemistry, visible enough to track with our instruments, a moment that will not recur. In a very real sense, we are the only observers 3I/Atlas will ever have, the only witnesses to its brief flowering, the only intelligence that will ever wonder about its origins, analyze its spectrum, debate its anomalies. That responsibility sits heavily. We owe it to the comet and to future generations of scientists to learn everything we can while we have the chance, to collect every photon, analyze every spectrum, model every trajectory, to preserve the data for decades and centuries, when new theories and new technologies might reveal insights we cannot imagine today. The nickel anomaly might be solved next year, or next decade, or never. But the observations will remain. The data will outlast us. And someday, someone will look back at this moment and know that when a messenger from the stars arrived, we paid attention. The nickel is still glowing. As 3I/Atlas moves outward, catching the last rays of our sun, the fluorescence will continue. Nickel atoms, liberated from their molecular prisons, will absorb ultraviolet photons and re-emit them as visible light. The signal will grow fainter with distance, dimming below the detection threshold of even our most sensitive instruments. But the atoms themselves will remain. Nickel forged in a supernova explosion billions of years ago, incorporated into a protoplanetary disk around a star we will never identify, locked into volatile compounds by chemistry we do not yet understand, released into space by the warmth of our sun, the only star this wanderer has visited in perhaps 7 billion years. Those atoms are now part of our solar system, in a sense, scattered through the inner planet's region, gradually dispersing, eventually mixing with the dust and debris that fills interplanetary space. In a few thousand years, some of them might fall to Earth, carried by the solar wind or swept up by our planet's gravitational embrace. This is how the galaxy shares its materials, not through deliberate exchange, but through the patient drift of comets and asteroids, carrying their chemical treasures from star to star. The iron in your blood was forged in ancient supernovae. The oxygen you breathe was synthesized in the hearts of massive stars. Every atom in your body has a cosmic history, a journey through space and time that predates the Earth by billions of years. 3I/Atlas is a reminder of that heritage, a physical connection to the vast processes that shape the galaxy, a piece of another world delivered to our doorstep by gravity and chance. We are made of star stuff, as Carl Sagan famously said. 3I/Atlas is a reminder that the stuff keeps moving, keeps circulating, keeps carrying information from one corner of the galaxy to another. Its nickel atoms will join the cosmic inventory. Its water molecules will eventually sublimate entirely, adding to the thin haze of hydrogen and oxygen that pervades the solar system. Its dust grains will scatter sunlight, contributing their tiny fraction to the zodiacal glow that illuminates the night sky. In this way, 3I/Atlas will become part of us. Not in any mystical sense, but in the literal physical sense that atoms do not care about boundaries. The material from an alien solar system will mix with the material from our own, indistinguishable, interchangeable, united by the chemistry that operates everywhere in the universe. What does it mean to be visited by a messenger we cannot fully understand? Throughout human history, we have looked up at the sky and wondered. Ancient peoples saw patterns in the stars and told stories about them. Medieval astronomers tracked the wandering planets and tried to divine their influence. Modern scientists build telescopes to peer deeper into the cosmos, hoping to answer questions that have haunted our species since we first became capable of asking them. Are we alone? Where did we come from? What else is out there? 3I/Atlas doesn't answer these questions, but it proves that the universe is connected in ways that our ancestors could not have imagined. Material from distant solar systems can reach us. The atoms forged in alien stars can fall into our telescopes, can be analyzed by our instruments, can become data points in our scientific papers. We are not isolated. We never were. The nickel anomaly reminds us that we still have much to learn. The chemistry of 3I/Atlas is different from anything we have seen before. It challenges our models, confounds our expectations, forces us to consider possibilities we had not entertained. That is the essence of scientific discovery. Not confirmation of what we already believe, but confrontation with what we do not yet understand. Some people found the nickel anomaly frightening. The suggestion that it might indicate alien technology touched something deep in human psychology, some mix of hope and fear that has attended every unexplained phenomenon since the first hominid looked up at a comet and wondered if it was an omen. But scientists found it exciting, not because they believed in alien spacecraft, but because they recognized an anomaly when they saw one, an observation that does not fit, a data point that challenges the consensus, a puzzle that demands explanation. That is what 3I/Atlas represents. Not an answer, but a question. Not a destination, but a door. 3I/Atlas has given us a gift, a sample of material from another world delivered across billions of years and countless light years. The nickel anomaly is the wrapping paper, strange and puzzling, and not quite what we expected. The gift itself is the reminder that we are part of something larger, a galaxy full of worlds, each with its own history, its own chemistry, its own story, and maybe, just maybe, its own questions about what might be out there, drifting between the stars. When the comet has faded from our view, when the last observations have been archived and the last papers published, we will still have those questions. They will drive us to build better telescopes, to develop new theories, to wait for the next interstellar visitor, hoping it will bring more clues. The sky is full of messengers. 3I/Atlas was just one of them. Others are coming. Some are already here, moving through our solar system undetected, too faint or too fast for our current instruments to catch. The Vera Rubin Observatory will find them. Future missions will study them. Perhaps someday we will reach out and touch one. Until then, we have the data, we have the images, we have the spectra showing 22 nickel emission lines blazing against the darkness of space. We have the mystery. And that mystery, unresolved and humbling, is the truest gift of all. A reminder that the universe is bigger, stranger, and more wonderful than we imagined. A call to keep looking, keep asking, keep wondering. 3I/Atlas has passed through our solar system and moved on. But the questions it raised will stay with us forever. Look up tonight. Find a dark place, away from the lights of the city. Let your eyes adjust to the darkness. The stars you see are suns, many of them circled by planets, most of them surrounded by debris clouds of their own. Some of that debris has been ejected, scattered across the galaxy, carrying chemical memories of worlds we will never see. One of those wanderers passed through recently. It carried nickel without iron, a signature that made no sense, a puzzle we have not yet solved. It will not be the last.